Okay, so this is our exam one review. Yay, yay. There is quite a bit of information packed into this first exam, which is why I broke it up this way. Might be a little bit more manageable than if we kept going. So kind of just to give you a rundown of what to expect, let me get rid of my meeting controls because that's really annoying. Okay, so this is kind of like a mock test or a practice test as far as layout goes. So on your guys' exam, usually I'll put these in the sections that they actually go with. So word bank would be with terminology, and the formulas would be with any calculations that you might need to run. I will also post this document here that has the equations and the word bank just separated from everything else. That way you could always open it in a separate window if it's easier to kind of keep track of stuff. So these are two resources. What they are here is exactly what's going to be on the exam. Okay, so remember I told you when I give you equations, I don't put what they're actually equal to as in terms of the variable you're solving for. So we'll go through these. Word bank, this is terminology that I think is relatively important. So you'll have a section in the exam that is pretty much fill in the blank answers. Sometimes it might be a better format for me to put a short answer if you're listing items. But generally, you'll have options that or questions that are either giving you a scenario and it's more of an applied use of terminology, or you'll have something that's a little bit more direct in terms of like blank is the, and then I give you the definition. Okay, so a little bit of a mix in there. The next section of the test usually, or another section, it's all randomized to shuffle around for each student. So your order will be different than other people in the class, but usually there's kind of like a conceptual scenario section where I give you a research example and then you identify certain pieces of information about that. For tests 1 and 2 specifically, you'll usually have a written calculation section where you can use like a piece of scratch paper or you can use Excel, but you're manipulating any of the equations that we've been working with so far. And then there will typically be a third primary section that the terminology and Excel SPSS data stuff, hands down, always have a section on the exam. Calculations and scenarios always have a place on the exam. Calculations are kind of up in the air, so just so you're aware. But this section primarily represents the activities that you guys do, and usually ends up having the most points assigned to it on the exam, which is why for studying, I encourage you to redo the activities just to make sure you understand, you know, like how to copy data, how to freeze cell references, so that way you make sure your formulas are calculating what they should be. But that's this section, and I think that's all I have on this practice. So you get a good sense of how I might ask questions. I think I went through this and minimized any wording issues, but we will run into them if they exist. So, all right. Anyways, first, let's start off by identifying the formula since that's the first thing on the list. So if you think you know the answer to a question, I'll pull up my chat transcript over here so I can see people answering. But if you think you know the answer, go ahead and put it in the chat, or you can just shout it out. I have limited abilities on what I can have on my screen at one time. Typically it gets kind of crowded. I can try something different. If you give me 1 second. I want to see if I can. Yeah. Okay. I am able to use my iPad as a second display. It's a little bit laggy, so hopefully that doesn't interfere with anything, but that might be the same.
Natalie?
Yeah.
What is the second Word doc you have open? E1 equations? Is that just the equations for exam 1? And
Yeah. So
posted?
yeah, what's on, it's not posted in this week, but whatever is in here is in your review stuff. I just put it on the side so you guys have a reference. It will be available during exam week though. Yeah, Beachboard is kind of weird when I post things twice, so I reserve it for exam week. Yeah.
And then Natalie, you're gonna post the answers to that exam 1 review questions later this week. Are you? I guess this question is.
I won't post the answers. People have to watch the video over again if they want the answers. I make you work for it.
Oh, like you posted a video to go along with all those questions down below?
Yep.
Oh, my bad. I'm sorry. Thank you.
Yeah, so it'll be similar to like regular lecture weeks where people will get the recording if they didn't show up, or you guys can just rewatch, and I'll put in like bookmarks or content markers so you can navigate through. But yeah. Okay, I think I have everything set up in a way that I will not screw things up. So let's look at our formulas first. What is this first formula calculating?
Isn't that simple frequency?
As a simple frequency distribution percentile. Okay, so
yeah, it is percentile.
Right, but it's if we want to be a little bit more specific, it's the calculation for an exact percentile of a simple frequency distribution, right? So if we're given sample data, regardless of what the shape of that data is, we just want to know what is the percentile of this person in the sample. That's what this equation will give us. Okay. What about the next one?
Oh, I had a quick question about the CF.
Mm-hmm.
You use the one in the same row as the score you're looking at. You don't do the thing where you do the one above it.
Correct. Yeah. So this one is just like in Excel, you could say count if less than or whatever the units are. It could be greater than, but whatever the direction worse than the score you're interested in is, you could say count if less than or greater than or equal to a given that raw score, and that'll give you the cumulative frequency at that score. Or if you have like a simple frequency distribution where your data are discrete, like when we did like the pull-up examples where it was like 3, 4, 5, 6, 7, and there wasn't decimal values mixed in there, you could just calculate cumulative frequencies like we've done before, where you start at the worst end of the distribution, right? Whatever you determine that to be, and then you just add the cumulative frequency to the frequency of the next row, right? And you just keep moving down the table. Okay. But yeah, the cumulative frequency in the simple frequency distribution equation is different than the cumulative frequency in the grouped frequency
Yeah,
distribution.
is that exact percentile in the group frequency?
What was that?
I said, is that exact percentile in the group frequency? Is that, would that be estimated?
This is
Percentile.
exact.
Okay. And that's when you have a range of data?
Correct. Right, so if we were looking at using pull-ups, right, if instead of looking at if like how many people did 3 versus 4 versus 5, we could say how many people were able to perform 5 to 10 pull-ups, and then 11 to 15, or however we decide to orient our intervals, right? But the interval size is indicative of groupings that are small ranges of the same size. Okay. What does this one calculate? This one's kind of easy.
Z-skew?
Z-skew, right? So this is one of the ways that we assess distribution shape. Okay. So this would tell us if we have any extreme scores to the right or the left of the mean. Okay, by assessing the sample shape compared to how that shape might look on a population, right? So this bottom part is the standard error. You guys can use little n or big N. Either notation means the same thing, okay? Because I've kind of put a disclaimer. Assume all calculations are for samples, so n just represents the sample size. Okay.
If that came out to less than -2, it'd be skewed left, and if it was greater than +2, it'd be skewed right.
Yes.
Gotcha.
Okay, and then similarly, we can just, you guys are smart cookies. All right, so this would be z-curt, or z-score of kurtosis, right? And kurtosis allows us to assess the quantity of extreme scores. Okay, so if we have positive kurtosis, that means that there are a lot of outliers, right? It kind of creates those low tails with a high peak in the middle. Okay. So that would indicate we have a lot of outliers if we have positive kurtosis. If we have negative kurtosis, which we would consider less a z-curt less than -2, right? Then that would mean our tails are floated off of the axis. Okay. In which case we have little to no outliers because all of our data are kind of on an even distribution. Okay.
So you said you want to have a low peak or a high peak?
For which one?
For
Or
kurtosis.
for kurtosis, you want a normal shape. So
Okay.
not something that is like a steeple, but also not something that's like an anthill. If that makes sense.
Gotcha. Thank you.
Yeah. Okay. What's this one over here? Standard deviation divided by the mean times 100.
The coefficient of variation?
Coefficient of variation. Okay, so it's one of our standard scores, and it allows us to compare different units of measurement in terms of their variability. Okay, does anybody remember how to determine high variability from low variability? If you're comparing two values or more than one value?
Isn't it the lower percentage is less variability?
Mm-hmm. Right, lower percentages mean less variability, higher percentages mean higher variability.
Could you also use standard deviation then to figure out like how much variability?
Standard deviation is a measure of variability, but it's always adopting the units of measurement. So if we were measuring people's height, like in centimeters, we could say individuals are, I should not have used centimeters because I cannot do metric conversions in my head, but maybe we'll use inches. So like say we're measuring females, like average height is usually between like 5'3" and 5'5". Maybe that's on the short side. I don't know. But we could say like the average is 64 inches plus or minus 3 inches, right? But the plus or minus, the standard deviation always adopts the units of the measurement that you're actually taking. So that's why we use coefficient of variation. That way, if we were comparing how much variability exists for height, which is measured in inches, versus weight, which is measured in kilograms or pounds, versus yada, 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 yada. Okay. And then what's this last one in the middle?
Z-score.
Z-score, right? This is what we covered last
Of the sample, right? That's of a sample.
Sorry, your video cut out.
That's Z-score of a sample. That's not Z-score of a population, though.
So when we find a Z-score, this one is going to be a sample because we have an X bar and an SD. You can find the Z-score of a population, but we didn't cover. I gave you guys an equation in the lecture, but all of our examples, as far as calculations go, will be for samples. If it was for a population, X bar would be replaced with mu, and the SD would be replaced with the little baby sigma triangle looking symbol. So, all right. So those are our equations. Cuckoo, cachoo. For our word bank terminology questions, I'm actually going to skip this part real quick because I think procedural stuff is probably a little bit more important to cover. So if you want to skip down to the conceptual scenario area, we'll do that part first. Okay, so I've given you guys a scenario that says you have the following research question. What is the effect of carbohydrate, caffeine, and carbohydrate plus caffeine mouth rinsing on intermittent running performance in collegiate male lacrosse athletes? Okay, so in this research question, what do you think your independent variable or variables, if there's multiple, what do you think that would be?
The independent variable would be carbohydrates, caffeine, and carbohydrates plus caffeine.
Right, so that would be, we could simplify by saying mouth rinsing solution. Okay. And then carbohydrate, caffeine, carbohydrate plus caffeine would be 3 levels or 3 groupings that we might use on our sample or samples if we have multiple. Okay. What type of data would this be representative of? You have 4 options. Go ahead.
I was gonna say, what do you mean by that? Like nominal, ordinal, ratio, like that?
Yeah.
It's mutually exclusive, so I'd say nominal.
Mm-hmm. Right. So we can say nominal. I also accept, well, for this exam, usually I like people to be a little bit more specific. But you could also put non-parametric data as well. I would not mark that wrong. Okay. But it's nominal because we are creating categories, right? So let's say we sampled 30 people. We put 10 people in the carbohydrate group, 10 people in the caffeine group, and 10 people in the carbohydrate caffeine mouth rinsing group. Okay. So they're how we categorize people within our study. What is or are the dependent variable or variables?
Running performance.
Running performance. Okay. And then what type of data might we use to measure that?
Ratio.
Ratio, right? And I would accept ratio, parametric, or in Excel sometimes, or not Excel, in SPSS sometimes referred to as scale data. Any of those answers would be acceptable, right? So maybe running performance is measured by, maybe we give them a task like how fast can you run a mile? And then their performance is measured by the time they can run a mile, right? Sometimes the examples I give you guys are a little bit arbitrary. That way it gives you a little bit of wiggle room. So I can accept multiple answers if people interpret the question differently. Okay. Is our test fill in the blank? No multiple choice. Sorry. It'll be very, very similar to this format, except it'll be in a beach board quiz instead of a Word document. But good question. No multiple choice.
How many questions will there be?
That is a good question. I don't remember off the top of my head because I still need to finalize questions on your guys's. There were some questions last semester I wanted to toss out. So I'm not 100% sure. But usually it's like around 30. Something that's somewhat equivalent to about 50 to 60 points. So you still have like a good opportunity to miss points without completely screwing yourself over. So then let's look at, oh no, that's coding. We don't want that. All right. So based on this research question, what hypothesis would be statistically tested for? So you have a choice, two choices, null hypothesis or a research hypothesis.
The null.
The null, right? It's that innocent until proven guilty scenario. So typically when, like if we're looking at correlations, we would say there's no relationship. Or if we're looking at ANOVAs or t-tests, there's no effect, right? In this case, the null hypothesis, since we're looking at an effect here, right, we would say the null hypothesis written out is that there's several ways you can write this. I'm going to choose my favorite way, which is that mouth rinsing solution has no significant effect on running performance. Okay.
Natalie, what would be an example of the research hypothesis?
Mouth rinsing solution does have a significant effect on running performance.
So then could you say either one?
No, because the hypothesis that's statistically tested is always the null. So in this question, we're identifying the technical name of the hypothesis, so that's null hypothesis. And then writing it out would be how you would interpret the null hypothesis, or how you would formulate the hypothesis based on the variables you are given. Okay.
Okay, so then if you said, if instead of mouth rinsing solution, it was like carbohydrate intake 30 minutes before exercise, would it still be null?
So if there's like a time component attached to it, or I don't know if I understand your question.
Yeah, like what would turn this into an alternate research hypothesis?
It would just be that none of these have an effect, or like one or all of them have an effect. So,
Okay.
because we're comparing groups, right? So we want to know, is the carbohydrate group different from the caffeine group, different from the carbohydrate and caffeine group when we assess running performance? And so the null hypothesis would say that each of those groups are going to have fairly equal running performances. So let's say we'll keep the mile time as our running performance dependent variable, right? So null hypothesis says that the running time for carb group is the same as the caffeine group, which is the same as the combined solution group, okay? Alternate hypothesis, or your research hypothesis, would say that there's at least one significant difference between each of those groups. And we go into this more when we actually get into ANOVAs. So we won't get into like the technicalities of it too much. But generally, null hypothesis is going to say there is an effect, or null hypothesis says there's no effect or no relationship. Research hypothesis will say that there is an effect or there is a relationship. Kind of just depends on what you're looking at. Since we specify there's an effect here, that is what goes into your null. Okay. But remember that null and the research hypothesis are mutually exclusive, right? And we can have a directional hypothesis or non-directional hypothesis. Wait, have I covered that with you guys yet?
No.
No, that's coming after the test. I got ahead of myself. I got excited. Okay, so never mind. They're just that they have to be mutually exclusive. Okay, so if mouth rinsing says that there is no effect, the research hypothesis says that there is an effect. If we specified a direction of the change we are expecting, let's say we think that the carbohydrate group is going to have the best running performance, right? We could, null hypothesis would say that there is no difference, right, between groups. Research hypothesis might say the carbohydrate group is going to have a greater effect on running performance than caffeine, or the carbohydrate and caffeine. So you see how they're mutually exclusive, okay? All right, so going into the interpretation of p-values, which we did just a little bit of in the first lecture, okay? If the results show there are a significant difference between mouth rinsing solutions with a p-value less than 0.01, this means what?
We accept the null hypothesis.
We reject it.
Wait, I don't know if multiple people were saying stuff. I heard an accept and I heard a reject.
Yeah, I
Right,
think we
right.
reject.
Blah! I can't distinguish what people are saying. I'm so sorry. So test shows there's a significant difference with a p-value of 0.01. What does this p indicate? We would reject the null, right? So we could write that. Reject the null. I had a stats teacher. She was Chinese. And she would always be like, reject the null. And I loved it. So I always say that now. But anyways, reject the null. And then what does, so there's a couple ways we could write this, right? If p is less than 0.01, that basically means that we have a really small probability of error. Okay, so yeah, Morgan, I think you answered the question that I asked before. What does p represent, right? It's what are the chances that we have an error in the effect that we're trying to prove, right? So in this case, we could write the results a couple of ways. Okay, so we could say, maybe I'll write it this way. Just write the opposite of what we wrote above, right? Mouth rinsing I can't spell. Solution has a significant effect on running performance. Okay. We could say there is a significant difference in running performance for different mouth rinsing solutions. Okay. We could also say there is less than 1% chance that the means, I'm just going to shorten that the means of running performance for each mouth rinsing solution what is English? There is less than 1% chance that the means of running performance for each mouth rinsing for each, maybe put this, of the mouth rinsing solutions are equal, right? Because that's essentially what the null hypothesis is saying, right? Mean of carbs is equal to the mean of caffeine, which is equal to the mean of carb plus caffeine. Okay. So basically what the null hypothesis would say is that given the p-value 0.01, right, we can always translate this to a percentage, right? There's less than 1% chance that the null is actually true. Okay. So a plethora of options to choose from, but all would be correct. So pick the one that makes the most sense to you. I think this bottom one probably most directly answers the question the way that I worded it, because I already told you there was a significant difference. But essentially, if that happens, you reject the null and then you accept the research hypothesis, which is the opposite of the null. Okay. Someone had a question?
I have a question. What would the P have to be to accept the null?
Typically, we'll go over this 2 weeks from now. Typically, we set an alpha, which is the amount of error we're willing to accept. Usually, this is going to be 0.05, meaning that we accept a 5% chance of error, or 5% chance that our results are due to error, with a 95% level of confidence that our results are representative of the actual difference between groups. So usually there will be an alpha level that you set prior to assessing your p-value. Okay. So if our p-value, let's say our alpha that we set for ourselves was 0.05, and our p-value came out to 0.08, right? The amount of error we were willing to accept was 5%. 0.08 indicates that there's an 8% chance that we made an error, right? So if we have an increased probability of making an error, or increased chance that our results don't reflect differences between our groups, then we want to keep the null and accept it as the law. Okay. All right. Any other questions on scenario type situations?
I still kind of don't understand what we would use. Like if it's saying what hypothesis would be statistically tested for this study, when would be like research hypothesis? Would we always just do the null first, and then when you're rejecting the null, that's the research hypothesis?
Correct. Right. So everything is centered around the null. So anytime,
I'll
whether
look
you're
into
running a correlation, a t-test, an ANOVA, a MANOVA, a MANCOVA, an ANCOVA, and other variations, okay? Doesn't matter what test, the hypothesis is always true until you prove it wrong, right? So if your p-value is greater than the amount of error that you're willing to accept, you say, I accept the null hypothesis because there's a chance that I was wrong and I don't want to be wrong. If your p-value is less than the amount of error you're willing to accept, there's a good chance that you are right in your statistical significance that you're showing, okay? In which case you would reject the null and say, the null is not right. This is the actual effect that I found in my data, okay? But you always test the null. Any other questions on this one? Okay, so let's go to our calculations then. Okay, and then this one, what we're gonna end up doing is copying and pasting this into Excel, unless I already have it pasted in there. I can't remember now. But what type of distribution is this?
Group frequency distribution.
Grouped, right? My computer is lagging. Come on, there we go. Group frequency distribution. How do we know that? Because our categories are in groups, okay? So the next question is, what percentile does a value of 27.2 have? I need to probably be more specific and say exact in here. Okay, so if I want an exact percentile, what method would I use to calculate what I'm looking for?
Wouldn't this be like the x minus L over I, the group frequency percentile equation?
Yeah, this doodad over here on the left where my cursor is. Okay, so let's go into here. I left a tab open for other calculations. That way we can just mess around. Doo-doo-doo. Okay, and that's really small. What? Wonder if I can just... Screen sharing always makes things go so much slower. I'm sorry. Okay, there it goes. No, 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 no. All right, well, you know what we're gonna do? That's not working either. Let me stop sharing real quick. Oh my God, okay. I'll stop sharing and then I'll reshare. Sometimes that is helpful. Okay, let's just go with that. This I want to make bigger so we can see it. Okay. What steps might I do with this? Or how might I reorganize my table so I can use a formula in Excel?
You make a lower and upper bound.
Right. So I'm just gonna erase this, but it's vertical jump, right? So I can make a lower and an upper column and then say, what is my interval, right? It's 12 to 14. So I can put 12, 14. That creates kind of a pattern for Excel to recognize. And then I can say, drag it down, right? And now I have all of the lower bound values. For my upper bound, I've specified 13.99. 15.99. Again, I've created a pattern, and then I can copy it down. This is driving me nuts that they're not all the same font, so I'm going to change it. Okay, our frequencies have already been calculated, so that's cool, right? And then we need a cumulative frequency column. Okay, so where would we start on our chart? At the top or at the bottom?
Top.
The top, right? Because it's like our worst score. It's the lowest jump height. So what would the cumulative frequency be at this top one?
2.
2, right? And then underneath that, the way we calculate it the rest of the way, or rest of the way down the distribution, is we say equals. Oh my God, my computer is not having it. Okay, we do equals the cumulative frequency that exists in the cell above, right? So that's where 2 was, so D4, plus the frequency of the group we're adding on. Okay.
So when we take the exam, are you gonna have an Excel that already has like this group frequency in it, or do we have to create this ourselves?
No, usually I'll give you everything you need in the Excel spreadsheet to save time. What
so
I
have like a link in the quiz.
Huh?
So like in the exam, like after like you say the question, you'll have like a link, and we just click on that, and that brings up like the Excel.
No. So I'll give you a separate Excel file, and then in the exam, I'll say go to this spreadsheet tab, and then I'll give you a list of questions to like answer based on any calculations you might run in that tab. But I tell you exactly where to go.
Do we have to turn those into Dropbox? The calculations that we do on the Excel?
Nope.
Oh, okay, it's just like scratch paper kind of.
It's basically like scratch paper, yeah. Okay. So we've got kind of this copyable formula that we can use to calculate the rest of our cumulative frequencies. Oh dear. Okay. So we can see we have 100 people in our sample, right? I had a raw score of 27.2 that I want to find my percentile at. Okay, so P would be equal to, we have 4 parentheses, okay? And chat box, got it, okay. So we have 4 parentheses, okay? What goes in the first set of parentheses?
Your actual values of 27.2
Mm-hmm.
minus the lower bound of like where it falls into like that group.
Right.
So it'd be.
So in here I can say, oh my goodness, what is happening? My arrows don't work. Hold on. This is dumb. Equals. There we go. So I'm referencing my X value, which is 27.2. Okay. Oh my God. There we go. Okay. And that's going to be subtracted from the lower bound of the interval that it exists in. So 27.2 would lie between 26 and 27.99. Okay, so I would put 26. Okay, that's divided by my interval size, which is
2.
2. Okay, how do we find that?
Upper bound minus lower bound.
Upper bound minus the lower bound, right? So we can take 2 adjacent groupings, right? Say 14 minus 2, that gives us our interval size, right? So 2. Okay, So that's kind of the first chunk. And then what comes next?
Times the frequency.
Times the frequency. Okay, which is 10. And then we add the cumulative frequency of the group worse than where our X value is located. So that would be where 71 is, right? Because worse than is going towards the top of the table. That completes our numerator. And then we would divide by our sample size, which is the highest cumulative frequency, so 100. And then we can multiply by 100 to give us our percentile, right? And you don't have to use cell references. I just like to click around so that I don't make any numerical value errors, but you are free to, put 27.2 minus 26 times 10 plus 71 divided by 100. You can use those numbers, totally fine, okay? But if I press enter, we see that we have a percentile of 77%, right? So we could insert that in our answer sheet. And the way that we could word this, a couple different ways, right? We could say that a person who has a vertical jump of 27.2 is at the 77th percentile. Interpretation of that means that they have scored better than 77% of the distribution, right? Or 77% of the raw scores lie below their raw score, okay? Does everyone feel okay on this process?
I just had a quick question. So you know how we used 71 as the lower bound when we were doing the equation?
Mm-hmm.
If we were doing, or I'm sorry, it was the cumulative frequency of the group before it, the little green box.
Mm-hmm.
So if you are starting your cumulative frequencies like from the lowest score and it's at the bottom,
Mm-hmm.
would you still, so in that case, you'd go to the one below it instead of the one above it since it's the worst score?
Right.
Okay.
Yep.
Got it.
Mm-hmm.
Thank you.
You're welcome. Okay. So we can go to our Excel SPSS stuff here. Okay. In Excel or on your exam, I'll give you a figure in an Excel sheet. This one, it was just easier to read the numbers here. Okay. But one of our questions, or the first one, asks, what is the median of the data set shown in the figure? How would we find that? There it is.
In like Excel or just like in general?
Either or.
I mean, just the middle number. So you have to write all those frequencies out, each number, and then find the middle one. If it's even, the even amount of numbers, it's like add the middle two, divide by 2.
Mm-hmm. Right. So there's several ways that we can go about this. We could say, how many values are there total in the distribution? So in this case, we would be counting frequencies. So there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because these all occur at frequencies of 2, right? We could count how many values are in the distribution, or we can create, I'm going to do this in Excel and adjust my screen so I can see all of the values in the table. Oh boy, it's going slow today. All right, so I could list out, how many of each value we have. So we're starting at 11, which there are 0 scores at, so I don't need to report anything. There is one frequency that occurs at 12. We put 12. No frequencies at 13. One frequency at 14. Okay. 16 has one. 17 has one. Okay. 18 occurs twice, or 18 through 21 occurs twice. So we can do 18, 18, 19, 19, 20, 20. Ew. 21, 21. Okay. 3 22s. 3 23s. Okay, there's 5 24s. I could say 1, 2.
There's no easier way to do that in Excel.
Off of a figure, no.
Gotcha.
Yeah, unfortunately. 25, there are 6 of these. So 1, 2, 3, 4, 5, 6. Okay, there's 26. There's also 6.
As you write these out, would you say that if you could pretty much do this entire like review without looking at notes and be able to hammer it out like with Excel as well, like you'd be pretty prepared for the exam?
I would argue that's probably true. This isn't comprehensive by any means. It's just to give you guys an idea of what to expect. So there may be some things that aren't included in this that would be important to know.
Gotcha.
Okay. So once you get your distribution kind of like sorted out on how many times each of these values appears, you can calculate the median and the mean. Okay. The median being equals median. Whoops. Jesus. I'm gonna unplug my iPad because I think between screen sharing, it is a little bit too much for it to handle. Which sucks because then I can't see you guys, so we're gonna work with what we've got. But okay, so equals median. You can see the function pops up here, so you know it's a real thing. And then we can say, I want the median of this data. And then I can also calculate the mean, which I do using the average function. I don't like that many decimals. So typically on the exam too, I'll tell you how many decimals to report. So pay attention to that. Makes grading easier for me because usually those will be in like short answer questions that'll automatically be graded based on an answer key bank that I provide the test. Okay, so in this case, our median would be 24. And our mean would be 22.98. Okay. What if I asked you the mode?
It'd be 25 or 26.
25 and 26. Both of these would be the mode because they occur the most frequently. Okay, and they occur at the same frequency. So that would be acceptable, 25 and 26. Okay. Based on this histogram, are the data positively skewed, negatively skewed, or relatively normal?
Negatively skewed.
Negatively skewed, right? Because the tail is below where the mean of the distribution should be located, right? Which is usually associated with where our highest frequencies are. If it was positively skewed, we would get kind of the opposite of this picture.
Can you determine the kurtosis from that as well?
Not as easily now. My guess, if we ran stats on this, like in terms of finding the z-curt, there might be a slight chance that we have positive kurtosis because you can see there's kind of higher frequencies of these outlier values. But I can't say for sure.
So the more outliers, the more positive the kurtosis is, the less outliers. So if it's more of a bell shaped, the more negative kurtosis you're gonna have.
Yeah. And the negative kurtosis would be a flatter distribution. So if we cut off, let's say the distribution was these 4 values, that would be more representative of kurtosis because all of them are occurring at a similar frequency. Okay.
Gotcha. Thanks.
Yeah. So visually, we know this has negative skewness because there's a tail tail to the left. That would be one way you could say it. You could also say that maybe not outliers, but because we haven't tested for that, but potential outliers below measures of central tendency. Okay. Tail to the left is probably the most common answer I would get on an exam. Right, or tail to the left of the mean if you want to be a little bit more specific. But this is a visual representation. Okay, I sometimes have people confuse that where I'll say like, what is the shape of the distribution? And they make a histogram or a bar graph and then just assume that whatever they see visually is what the shape is. Okay. If I ask you something related to calculations, that means you need to do the skew, skewness, standard error, and then the z-skew calculations. So we
can you double check the mean?
Yes. I could have input a value at the wrong frequency too, if you're getting a different.
I think, can you check if it's a 41 count? I think that's what it is too.
I'm missing a 23.
Okay.
That should fix it. Yeah. Hold on. Does that change anything for anyone? 1, 2, 3, 4.
Now you have 423s.
423s. Oh, there were 3.
You should have 320.
That was right. Okay, so that's not where I made a mistake.
You put for 18. Oh, never mind.
6. 1, 2, 3, 4, 5, 6.
I got 24 for the median too.
4.
Oh, you put 7 25s.
Did I? 1, 2, 3, 4, 5, 6. Ah, that's where it is. Okay. See, teamwork makes the dream work.
Okay.
So if I take that out, let me make sure this range is still the same. There we go. 22.9.
Yeah.
Is that more like it?
Yep.
There we go.
Thank you.
No, thank you. Okay, so if we're looking for shape based on calculation, we know we have to calculate our z-skew values. And remember, this is the one that we would actually use to determine if our sample is skewed or not. Okay, so to find the sample skewness, it's equals skew. And then we insert our data range. Oh, and that's not going to like me now. Hold on a second. We try again. Okay. My standard error, does anyone know how to calculate this one?
Isn't that just like the square root of 6 over n?
Yep. All right, so square root of 6 divided by n. If you know n, you could stick it in. If not, we can use a count function and say count all of the cells that have a value in them in a given range of data. And then to get our z skew, what do we do?
Isn't it just sample over the standard error?
Yep, sample over the standard error. Okay, so just divide those two. And we get a value that says negative 2.65. Okay, so based on our calculation, this is kind of the law in terms of what our shape of our sample is and if we were comparing it to a population, right? So do we indeed have negative skewness, both visually and based on calculations?
Yep.
Yes, we do, right? Because this is outside of the acceptable bounds of plus or minus 2 z-scores from the population mean, okay? So how do we know based on distribution calculations? We could say something along the lines of z-skew equals negative 2.5, not 5.6, 6.5, 6, we can round up, 6.6, negative, 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 negative. Woo, there we go, right? Which is outside the acceptable range of plus or minus 2 z's from the population mean. Something along those lines would work. Z's, like z-scores, you could also write z-scores. That also works. Okay, but it's different enough from the population, which we always assume is normal or normally distributed, right? So if it's different enough from the population shape, we can assume we have skewness in our sample. Okay. For the sake of just doing it, let's try kurtosis as well. And we'll actually see if it's kurtosed or not. Right, so similar procedures, equals kurt will give us the sample kurtosis. Standard error is going to be the square root of 24 divided by our sample size. Yes. Okay, and then we could say sample kurtosis divided by standard error. So in this case, we do not have kurtosis. Okay, remember I did say though, because there are kind of several smaller frequencies on this little outskirted edge that it would probably be positive if anything. And you see we have a positive number. Not quite enough to argue that we have positive kurtosis in our sample, but that's what that positive is reflecting, is this higher frequency of values that occur at low frequencies, if that is not confusing. Okay. Any questions on this one? All right. I feel like generally figures in these types of calculations are pretty straightforward. So let's go on to our next one. So this is what it would look like in the quiz. Use the data sheet, or use the data and spreadsheet titled Kin 263 to answer the following questions. All right, so we would go to Kin 263. We can see we've got some data in here. Okay. Question number 20 in this case asks, what would be the exact percentile for someone with a Planck time of 151 seconds within the sample? How might we figure this out? I'll just make note here that X is 151. Okay.
You can do this several ways, right?
Yeah.
Couldn't you just order the column down from least to greatest, and then just do the cumulative frequency at that score over the total?
You could do that. Okay. So suggestion was, let me get rid of my meeting controls real quick. Hold on. Suggestion was to filter the data, right? Organize them from like worst to best or best to worst, whichever, right? And then find the cumulative frequency at a given score. The other way I was thinking of is we could do a countif function, specify a range, basically gets at the same thing, it just does it without the filtering step. Okay, so I've specified a range, which is my blank times, and then I need to specify a criteria as it asks for in the formula. So my raw score is 151, and I want scores less than or greater than that value.
You want less than or equal to?
I want less than or equal to, right? Because percentile is values that are worse than the score of interest. Plank time, the longer you hold it, the better you do, right? So lower scores under this 151 can be considered worse than, right? So we could say less than or equal to, and we want it matching the criteria of 151, right? Or we could stick in our cell reference. That also works. Okay. So I stick that in, and it's not over. That gives me, so I needed an extra, let me do this real quick. We'll do it in steps because I originally was gonna do it all together, but this works as well. So that's a cumulative frequency. Okay. To get the percentile, we need the cumulative frequency divided by the sample size. So we could say cumulative frequency divided by sample size, which we can find out by counting. Okay. Whee! And then we can multiply that by 100 to actually get a percentage. Okay, we'll just let it sit there so people can fill in. I do these things kind of fast sometimes. So, right, so we found cumulative frequency of values that are less than or equal to 151. Take that cumulative frequency, divide it by the sample size, multiply by 100, and we get 65.59. So we could report that as our answer. Right, and this is acceptable because we just want the exact percentile within the sample. We don't care if it's normally distributed or not. Okay, 59%. All right. So then the next question is asking how many people can bench press between 110% and 119.9% of their body weight. How might we find this?
That'd be count ifs now.
Count ifs, right? Because we have two sets of criteria and we're trying to find a frequency or a number of individuals, okay? So I'm gonna just put some notes here so we know what we're looking at between 110 and 119.9, okay? So, yep, there we go. All right, so we would use a count ifs plural. We're looking at bench press, okay? So I take that range of data, specify my first set of criteria. Okay, so I'm gonna do this real quick so I can come out of this. If you wanted to create cell references, you could, or I could say 110 and 119.9. Oh my God, there we go. Right, And then within this, we can specify those cell references, which I don't know. I kind of think that's the easiest way, but it's up to you. Okay, so we specify the range. We want values that are greater than or equal to 110. Okay, so in our formula, we can put greater than or equal to, and my cell reference for, might have to use my arrows. Damn it. Why do you hate me? Hold on. It's not liking, it was blocking these, so I couldn't click on them. It was rude. Okay, so that's my first set of criteria. And then I can list my second set of criteria, which applies to the same range. But I want these values to be less than or equal to 119. What? And there we go. Okay, so now you're looking up in the formula bar because it jacked me over. Right, so 2 sets of criteria for the same range of data should give us how many values are between these 2 numbers. Okay, in an exam, I would be specific if I wanted you to include those values, because some of you are like, oh, if it's between, then you're not including, in which case you could say greater than F9 and less than G9, if those are your references. But I would say include these range values or don't include. I would specify.
Natalie, I have a question.
Yeah.
What does it in turn? It says you've entered too few arguments. Does that mean I missed a comma or something?
That or you're missing parentheses sometimes is another.
Oh, okay. So it just means like you left out something from the equation. Okay.
So in our answer, we would say 34. Okay. Next question is, which class measurement has the most variability? What might we use to assess that?
Is the coefficient of variability?
Coefficient of variation. Okay. So
yeah.
Close enough. It's a COV in my opinion. Okay. So what do we need to find the coefficient of variation?
Standard deviation.
Standard deviation and
The standard deviation mean.
Yeah, exactly. Okay. So that means we need to find the standard deviation of each group. So we'll have push up, can't spell, bench. Let's say runtime. I'll just put run and plank. Okay, this is the actual row of interest, just so I'm making that clear. Okay, but we need to find standard deviation and means in order to figure out what the coefficient of variation is. Okay, so standard deviation, we do STDEV, right? And then I can calculate the standard deviation for my push-ups. Mean you guys are familiar with, which is average. Right? And then our coefficient of variation equation is our, well, order of operations. It should pick it up. Should be standard deviation divided by the mean times 100. Okay, so you can kind of follow the colors. Standard deviation's in the numerator, mean is in the denominator. And then we get the percent of variability. Okay, I want to copy this, right? So I've got all my formulas set up. As I copy to the right, my references in the columns will also shift to the right. So always double check before you copy stuff, but should work. Okay. And then which group has, what did I ask you? Which group has the most variability?
Push-ups.
Push-ups, right? Or which measurement, rather. Okay. Push-ups has the greatest variability because it has the highest percentage. If I ask which group has the lowest degree of variability or the lowest amount of variability, you would say bench press because it has the smallest percentage. Any questions on that one? Let me open up the chat box. No chats, so I think we're doing okay. All right. So the last question on this is saying, assuming the data are normally distributed, what is the probability that a random person from this sample would be able to run a mile between, and then I left these blank, so we're going to come up with a value. Okay. So the first thing we need to know, just to preface for you guys, what is the min and the max of our runtime? All right, so somebody pick a value, just shout it out. Pick a value between these two numbers, 7.6 and 12.6.
10.
10. Then someone pick another number.
8.
8. Sure. Okay, so we're going to say x1 is 10 and x2, well, actually, let's do it in a numerical order. That would make it easier. 8 and 10, right? So these are in minutes, just so we know. Okay. If we are assuming our data is normally distributed, or we're saying we can make that assumption, what would we use to figure out this question, or what this question's asking?
Wouldn't that be the exact group frequency distribution equation?
Not quite.
You said estimated?
Yeah.
Okay. I didn't quite.
Z-scores.
So z-scores, right? If we can assume the data are normally distributed, then we want to do a z-score, right? We could also say, I could say, what is the estimated percentile that we pick a random person between two values? Okay, so if you see assume data are normally distributed, or you see estimate percentile, that kind of gives you a hint that you want to use z-scores. Okay.
Oh, but if you said percentile, then it's group frequency.
What? If I said percentile?
You said probability. If you said percentile, then it would be group frequency.
No, because we're assuming the data are normally distributed. So this is kind of the key phrase that you're going off of to understand that you want to use a z-score. Because we can only use z-scores when we have a distribution. So if we need, yeah, you're welcome. Right? If we need to calculate z-scores, what information do we need to know about our data?
The standard deviation.
Standard deviation and
the
mean.
The mean, right? And we're particularly interested in our runtime, which we've already calculated. So I'm just gonna put those values down here. So we have them. SD, and then we're gonna calculate a z-score. Okay. So the mean and standard deviation are here. I'm just gonna copy and paste. And copy and paste. Okay, so that I can use these as cell references. All right. So to calculate a z-score, I want to do the raw score of interest minus the mean divided by the standard deviation, which hopefully you can see this little purple box here. My screen covered it. Okay. And then we would do the same thing, so you can copy this over. We would do the same thing for the value of 10. Again, taking raw score minus the mean, divide by standard deviation. And you can see that we get these two z-scores, right? Which are going to be correlated with a certain percentile. So how do we find that percentile or that probability?
You look at the table.
We have to look at the table, right? So I'm going to find my table.
Well, exam, this table will also be presented.
Yes.
From you.
Mm-hmm.
Gotcha.
You guys will have everything you need. And if you don't have it, I'm available for questions during the exam, so you can always ask and I will make sure you do get it if you don't have it. Okay, so let's look up the probability that we would have a value at 8. And actually, I'm kind of glad this happened because if you guys think about runtime, and Excel is not smart in this sense, but I just realized.
Why didn't you round it?
Huh?
Why didn't you round those z-scores?
Oh,
Why
I could.
don't you? Oh, okay.
I could say I could put them at 2 decimals.
Mark us off on that, right? Like you saw like it was negative 2.55. If somebody found the percent probability at 2.55, would you mark them down?
No, usually I have like one. I usually account for rounding errors. So if you put negative 2.55, it wouldn't be marked wrong. However, what I do want to point out is that, oh my God, this is why I wish my iPad wasn't acting up today because I don't want to draw. What I do want to point out is where 8 and 10 actually lie on the distribution, because that's gonna affect this information here. So if we were building a distribution, we would put our mean in the center, right? Which is, I'm just gonna put 10, but it should be 10.53, okay? And then we would list values above and below the mean, okay? In terms of kind of what is the better end of our distribution versus the worse end, would you expect lower values or higher values up where the 100th percentile would be?
Lower values.
Lower values, right? Which is a little bit opposite than the examples that we've used before. And I don't think I would do this on the exam because that would be mean and tricky. But I'm gonna round up just so I don't have to write too many numbers. But the standard deviation is relatively close to 1, right? So in terms of going above and below the mean, remember, worse scores go to the left, better scores go to the right. So if my best time or fastest time is a smaller value, that means I actually have to subtract as I go this direction, right? And then I would add as I go in this direction because that means people took longer to run. So when you look at these values though, negative z-scores usually indicate something over on the left side of the mean, right? In our case, because these are smaller values at the right side of the distribution, we actually need to take the like the z-scores times -1 in order for us to find the actual percentile that is associated with these values. Does that make sense? I can't see people's faces, so that was kind of dumb for me to ask. But
yeah, so pretty much you're saying that like Excel's not taking into account that the lower scores are actually better.
Yeah.
Gotcha.
So it's something to be aware of, but like I said, on an exam, I would not do that to you guys. That would be ridiculously mean. But what we have to do is instead of taking the negative, just look at this and think it's a 2.6, positive 2.56 z-scores from the mean, right? Because if we kind of plot this, right, 8 is going to be here and 10 is going to be here, right? It's actually 10.53, so we should be just slightly, oh my God, it's so bad. We should just be slightly to the right of the mean, but the probability we're trying to find is this area here, okay? So with that being said, I'm gonna stop drawing and we're gonna go to our z-table. So we're gonna look up 2.56 first. So that should be 2.5, right? And then we go 0, 1, 2, 3, 4, 5, 6. So 8, or the value of 8, should have 99.48% of the data underneath it. Okay, so I'm just gonna write that in here, 99.48. Or you can put 0.9948, doesn't matter as long as you're consistent. Okay, I will put both notations, either probability or percentile, in the answer bank for these types of questions, so you shouldn't be wrong. Negative 0.53 we're treating as a positive 0.53 because that's where 10 would lie, or well, yeah, 10 in this distribution. Okay, again, I didn't use decimals, so just use your imagination. Okay, so 5.3 would give us a
Natalie,
of.
how come it's not negative 0.53?
So that's
Since
where
it's behind mean.
So that's what I was just saying, is because Excel is not picking up that smaller values are better in this context. And so they're going to say, when we ask,
oh yeah, okay, I know.
Yeah, the value minus the mean, that it's going to automatically return a negative value. But this is where these values would be located in this distribution. Okay. So 70.19 is the percentage of values that lie beneath 10. Okay. So how would we find this shaded area?
Subtract it.
You take the difference.
You take the difference. Exactly. Right? We say, I know that 99.48% lie at or beneath the value of 8, and 70.19% lie at or beneath 10. But I'm not interested in this blank section over here, right? So I would subtract the percentages, and that would give me what's left over in this blue area. Okay. So our answer would actually be 99.48 minus 70.19. which gives us 29.29%. Okay, so just for reference, we were looking between 8 and 10 minutes. And the percentile that we found that lies between those two values, you can either write it 29.29, or I would also accept 0.29 if you're reporting it as a probability. Either one is correct. I would just make sure, and we did this in lecture, and I also put a smaller video for reference on how to build a distribution based on a mean and a standard deviation. Make sure you know how to do this, okay? Don't do what I did and like use estimated numbers. So in reality, this would be 10.53 because that was the mean we identified. And then going above the mean, in this case, typically you add, right? In this case, we subtracted, but okay. I have the examples that are more aligned with what would be on the exam. So, and I would probably watch the videos.
You said just not to draw the bell curve? Like use it?
So if I gave you a bell curve and asked you to fill in, like if I gave you a mean and a standard deviation and I said what would exist at each of these tick marks, just make sure you know how to do that.
Oh, okay.
Mm-hmm.
Gotcha.
And then you said you would add? Or were you talking about the adding part?
So typically, this
okay, for the x-axis, I got it.
Yeah.
Okay, the x-axis.
So,
all right.
Just for notation purposes, I'm so sorry, this looks horrible. But either one of these notations would be acceptable. Okay, so 0 meaning that's where the mean is, plus 1 standard deviation, plus 2 standard deviations, plus 3, and then same thing on the other end. All right, so you can either use like z-score standard deviation notation, or you can use the raw score notation. Either one is okay.
But let's say your standard deviation was 2, those numbers would change, right? To 2, plus 4, plus 6.
No. So this is the number of standard deviations from the mean, right? Not the actual.
Oh, okay. So your raw scores would change. So 10, it would go 10, 8, 6, and then 10, 12, 14.
Mm-hmm.
Gotcha.
Yeah. But the actual like number of standard deviations or number of z-scores is constant.
Right. Gotcha.
Yeah. Okay. So I'm gonna move on for the sake of time to our squat data. Okay. And this says, in evaluating the distribution of the squat data, how would you describe the shape of it, and how do you know? Does anybody have any ideas on this one?
Do you have to make a histogram?
I'm glad that you said that. You would not want to do it in this case.
Oh, good.
Yeah.
You wouldn't want to do a histogram?
No. And this is why I mentioned it earlier, because I was saying that a lot of times people think if I'm looking at shape, I'll just make a histogram or a bar graph because it will easily kind of create an image so I know if it's skewed or not. But there are some times where a sample can be slightly skewed, but it would still be considered normal in terms of the population, right? Because we kind of have that plus or minus 2 cutoff. So if I ever ask you describe the shape, always default to performing skewness and kurtosis calculations. Okay. The only exception was up here where I said, how do you know visually? Okay. The visual representation gives you an idea, but it doesn't tell you the degree of skewness or kurtosis that you would have, right? So for this one, we're going to calculate or do our skewness and kurtosis calculations, which we've already gone through. So we'll just do them again because repetition is good sometimes. Z-skew, and then we'll do our sample kurtosis, standard error for kurtosis, whoops, and Z-kurt. Okay, again, these are the Z values are the ones that you're actually interested in reading. That's another common mistake is that people they kind of report the sample skewness or kurtosis, and that's not correct. Okay. So similar procedures to what we've used before, we're looking at squat data. So I'm going to do my sample skewness, find the standard error, which is the square root divided of 6 divided by the sample size. Okay, and then my z-skew is the sample skewness divided by standard error. We'll do the same thing for kurtosis. Whoops, equals square root. And I'm going through this quickly because we already went over these procedures. So if you need to review them, that is okay. Voila. There we go. Okay. So these are what I calculated. What do you guys think the shape of the distribution is?
Normal.
Normal. Why?
They're both between plus and minus 2.
They're both between plus and minus 2. Okay. So again, we're trying to see where does our sample lie, or what does the shape look like in terms of a normal distribution, which is the population. Okay. So our answer would look something like, actually I want to make it red so it pops out. The distribution shape is relatively normal. Okay. How do we know? Use values. Z-skew, which is 1.73, right? And, oh no, and Z-kurt, which we calculated as 0.07, right? Are within the acceptable bounds of plus or minus 2. Okay, meaning that they are similar enough to the population's shape.
Natalie?
Yeah.
Sorry, I had a question. I'm sure you went over this at some point, like either this lecture or before, but if one is over 2 and the other one is between the normal values, what do we do for that?
So hypothetically, let's say that this came out as plus 2, and this one came out as its value, okay? If this was the case, we would say that our distribution has positive skewness and no kurtosis.
Okay. And then in activity 3, there was a question, I believe like the first one, where it's asking which measurement did you use to see which one is not distributed normally, I think. It was like the first one. Would we be just picking the one that shows the most variability?
Ask me that question at the end because I don't have the activity in front of me, so I don't remember exactly what you guys were working on.
Cool, thank you.
Okay, but that was a good question, just in case there's, skewness is above or below plus or minus 2, and or kurtosis is above or below plus or minus 2. You give the shape relative to each measurement. Okay. But what I wanted to do real quick is to show what most people would do in a regular semester. Or at least it's a very common thing that people do, right? Is if I plotted this, you guys might jump to the conclusion and say, oh, that has positive skewness because there's a tail, right? And it's close, but it's not extending to to the point where we would actually argue there's positive skewness. So that's the reason, do the calculations instead of a chart. Unless I ask you visually, what do you see? That would be the only exception. Okay. Which sport has the highest mean max knee flexion angle? What do you think we might do for this? So we have a legend based on sports.
You do them average, but you only go up until like 1 per second.
Right. So, and we're only interested in the max knee flexion. So that's the nice thing about this compared to activities where you kind of have to do everything. You guys can just find, let's say these are averages of my sports, which are cycling, rowing, and mountain running. I'll just put MT run, right? And I can easily find the averages. Average, there we go. Cycling was listed as a value of 1. So I would take max knee flexion values up until I see the shift between 1 labels and 2 labels, because that means I'm switching sports. Okay. I can then find the average of max knee flexion for anyone who has the data label of 2. This is very similar to the coughing, wheezing, COPD question that you guys had in terms of chunking information. All right, and then last but not least, I can find the average of anybody who has a data label of 3, which indicates that they are a mountain runner. Okay, so which group has the highest mean knee flexion angle?
Rowing.
My rowers, right? So that would be my answer for that one. Rowing. What is the sample standard deviation of experience for rowers? I know I'm finding standard deviation. Okay. And I want experience is the column I'm interested in. Rowers is just the data label or the range of labels that I'm looking at. So standard deviation of experience of anyone who has a data label of 2, because 2 represents rowing. 1 more. Okay. So I get 1.2, let's round up, 1.28 years. And that would be my answer for that one. Okay. And then assuming the data are from samples that are representative of the population, meaning that they're normally distributed, okay, estimate the percentile for a mountain runner that can squat 122% of his body weight. So would we be using frequency distribution percentile calculations or z-score calculations?
Z-scores.
Z-scores.
Yeah.
Sorry, did someone else say something? I might have cut you off. Yes. So let's say x is equal to 122, right? And then we need to find the mean, standard deviation. Those go into making our z-score, which then we can look at the z-table to find the probability or percentile, right? And we're interested in, before I get too far into this, percentile for a mountain runner, right? So looking at mountain runners, that is a data label of 3, okay, in terms of what they can squat. So I'm gonna look for the average of mountain runners, which actually we already calculated, so I can just do that, right? Standard deviation will be data label 3, right, for all of my squat data. So you can see standard deviation of the range that associates with the value 3. Okay. Z-score I calculate. We've gone through this procedure already too, right? We would do the raw score minus the mean. Don't forget your parentheses because order of operations, right? Divided by standard deviation. Okay. This particular example is giving me a, why is that so high?
I think you took the wrong, mean. Oh no, now it's good. Oh, well, now it changed.
Mountain runners. Oh, these were the means of the knee flexion angle. I was like, why is it 4? That is ridiculous. So I'm gonna change the range to there. So this is the new mean, okay, 125, and that makes a lot more sense. Okay, so negative 0.56 is the z-score that we get. So that would tell us go to the negative z-table. And then I can look up negative 0.5, 0, 1, 2, 3, 4, 5, 6. And my probability is either you can report it as 0.28 or 0.29. Either one of those would be acceptable. Or you can do 28.77%. Okay. So that's what I would report here. Okay. Or as a probability, if we're rounding properly, 0.29. Any questions on that one?
Nope.
Awesome. All right. So the terminology I'll leave for you guys to work on independently. I will say a couple of notes on the terms reliability, validity, and objectivity. In different contexts, they can sound like they would be used the same. If you're unsure, you can always say reliability is consistency, variability is accuracy, and objectivity is looking at something without bias. Okay, so you can always rephrase things to see if they make sense. I will say that number 3 and number 4 have 2 different possible answers. Okay, so when we're looking at this example, inexperienced undergrads aren't likely to be as blank as graduate students when it comes to marker placement. Okay, one may not be as reliable, and they also might not be as valid. Reliable grammatically sounds better, but in terms of consistency, right, because they're inexperienced, that's where we kind of get that investigator error, right? They're not as consistent with marker placement, but they might also not be as accurate with the marker placement. So you see, if you kind of switch those words around, reliable with consistent, valid with accurate, it helps to make a little bit more sense on figuring out what you want. Okay. Same thing for number 4. Finding joint angles using video or motion capture is more blank than using a manual goniometer. Typically, we would say using equipment of any kind is going to be more objective than using human measurement, in terms of like you're making a judgment call on what you think the measurement is. Okay, so objective or without bias would be one of the options, but also motion capture is more valid and accurate than a manual goniometer. You might get similar values, but accurate or valid or objective would be 2 possible answers. And the exam will be the same way.
Couldn't reliability work? Because it's going to be more consistent as well.
Yeah.
Because with more accuracy comes more consistency, right?
Not necessarily.
Well, with a video camera, wouldn't it be more consistent?
Yeah, you could argue it that way. And usually I give you guys the benefit of the doubt. So if I'm like, it seems like they interpreted it this way, then I usually give you the point. But usually for these types of questions, I always have 2 possible answers. So if you're unsure, go with your gut, and then you're probably going to be right, because you have a 60% chance of being correct, pretty much.
On the exam, will we only like go to use each word once, or will you do it like where we use the same word like multiple times?
In your guys' exam, I believe I have it set up where words can be used more than once. Just because I incorporate questions on different types of data. So if I give you an example of like 3 or 4 different, like what type of data would force be? And you put ratio, and then another question I ask, what type of data would weight be? Also ratio, right? So in that sense, you can repeat words. I'm pretty sure I have it set up like that, and I don't think I'm going to change it. So yeah. Okay. Any questions on the exam as a whole? I'm going to stop sharing.